No, term A is 6B, right? So the other thing we discussed was how to actually, that procedures can return, procedures is return values. Now I skip back. Okay, some days are just not good days. I want to die. Let's see if we can use the wired mic. Okay. Friday. Yes, this Friday. Oh no, tangled with. All right. Seems to sort of work. So let's just think through this. Some days depress me. Okay. All right. So today we're going to talk about a slightly different, slightly related thing, which is higher procedures manipulating other procedures. Okay. So if you remember this example from week 2, right, whereby we had this patterns and then we can repeat patterns. Okay. So you notice in this example, right, this thing called pat here, right, that's actually a procedure. Okay. So this is an example of procedure being used as argument for procedure. And output, what's output? The output is a picture, right? Okay. So if you look at this whole example, what you see is this: you have n, which is the number of times to repeat. You put in a pattern. The pattern is procedure, right? That you apply on the picture, and then you put a picture. Okay, what happens? Out comes the picture, right? This is essentially the signature that you see for this particular procedure. Now, then you remember the sum term A next B, right? Okay, what comes out? The value, right? Okay, so this is another example of what happens in this higher order procedures. Okay, the next thing we covered last week was this thing called integral, whereby you put in a function, you put in the limit and delta x. What happens? You get a value out. This gives the integral of the function over AB. Then derivatives looks a little bit different. You put in a function g, okay, it comes out what? D of g, right, which is the function. Okay. Then Newton's method, right? You put in a function and the guess. Okay, out comes the value, which is the root of the function. Okay. Now, so this is what you just saw. Repeat pattern. You put in n pattern picture, and then it comes out a picture, right? Okay. For homework, okay, just make sure you understand this. Go and convert this particular pattern into this form. Okay, such that you put in n, you put a pattern, out comes a pattern. Okay, and then if you take a picture. So this is n pad. Okay, if you take a picture and you put it through the n pad, you will come out the picture. So such that these two things, these two pieces, is equivalent to the top. All right, that makes sense to you? So this basically helps you understand how you can put these things together, how you manipulate them, all right, and how they work. This is not bad. This might is not too bad. Okay. So the thing about the higher procedures is not to worry about definitions. Someone, I think it's dark, right? Who are you? Dark, right? You were talking about this, So essentially, the procedures, right? Higher procedures, they can be one of three things, right? They can take in procedures as arguments. They can cross out procedures as values, and they can do both. Okay. So this is the general idea of procedures. So the whole point of higher procedures is basically high order, so they're dealing not just with values, but they can actually manipulate procedures. This is actually it's very uncommon. Okay. Typically most languages, most languages support this, but then they don't usually do this sort of thing. So it's kind of cool. All right, and so in another example we're going to talk about today is functional composition. Okay, in math you've seen this thing, fg of x is fg of x, right? So essentially, the operator says use functions as operands, and then the result is a function. Okay, so the thing is that we have a simple way of doing this. It's called compose. Okay, so compose f of g, compose f with g is just lambda of x. Fg of x. So it turns out that f and g obviously are one parameter functions. That means this one parameter procedure. They take only one procedure. So what happens here is that this composition function procedure will take in the value x. Okay, you apply g, apply f, and then return the value. Okay. So okay, before while I'm talking here, you can take out your clickers just to make sure it works. All right. So the following, so suppose you have squared factorial, okay? So compose square factorial, okay? Okay, and you do square factorial 10. Okay, what happens? What's the answer? Okay, you return the same answer as square of factorial 10. So notice the following. Composition is not what? It's not commutative, right? Which means that you cannot do what? You cannot happily swap around the two pieces. Okay, unless the functions themselves are commutative, then you can swap with infinity. Okay, but typically the two guys, okay, so basically compose square of factorial, compose factorial square, they are not the same thing. Right? Okay? Okay, so now let's test understanding. Suppose, this is your foo bar thing again. Suppose foo is x, 2x plus 1, right? Bar is compose foo and foo. What is compose bar of 1? Hey, hurry up, click. Hey, don't anyhow click. 1 to 5 is here. Okay, and we will test again whether you're understanding, whether you know how to click or not. Okay, this figures. Jerome, you lose the clicker or not? You lost it? Then why did you send me email? Oh yeah, of course, because I haven't received it. Sorry. That's a good one. I have to receive it in my pocket. No wonder it doesn't. How cool that? Okay. Huh? The polling closed. Okay, let's try. Okay. Aha. Okay, so it works. Yes. No, it's okay. It's a little bit late. Okay. So the whole point of showing clickers is to make sure that you bring along. Okay. So today is another trial run. Anybody? Okay. Done. Okay. So we are done, and actually, it turns out I know exactly who is clicking. Okay. So if you are blur, we'll come and call you later. All right. So let's take a look. Whoa. Okay. So how? What's the answer? Okay. Because we are having a P tomorrow, so we are basically practicing, right? So we know who to win. Okay. Turns out obviously the guy who got the highest vote will win. So the answer is 31. Okay. So this one you can go and try it yourself. Okay. See what is the answer for this. Okay. Good. All right. So another foo. Okay. What is this procedure compute? Anybody? This does what? Factorial. Sure or not? B to the power n, right? Okay. Now, so the problem is that every single procedure you see looks like this form, right? It's a kind of recursive procedure. So this is actually e to the power n. Okay, so it turns out that you sometimes have to compute these kinds of procedures, which are functions which are like f n times. Okay, and so the thing here is this, right? The definition of ext t, which is exponential, can be obtained from this particular expression if you replace essentially this operators by star. Okay. And so suppose you do, okay, this is what you see as the typical exponential procedure. Okay. Suppose we find the following, okay, called rcomp, okay, which is repeated composition, right? So you can compose basically f on f. Okay, essentially you want to compose the f how many times? Actually, you compose f of them together, lah. Okay, so you need to basically apply the composition operator n minus 1 times, right? Okay, so this is the kind of analogy you see for repeated to the exponential. Now, so suppose this is the case, right? Rcomp f of n. Okay, so essentially, suppose I want to do rcomp square 3 times. Right? What happens here if you open up is the following. You will see that this becomes like this, right? Because you do this 1 time like this. 2 times like this, and then third time, whoop, 1, okay, 2, then the third time looks like this. So essentially, if you do the recursion, okay, it becomes rcomp of square, rcomp square, rcomp square, rcomp square of 0, right? But when rcomp something of 0 happens, you have this thing called lambda xx, which is what? It's the identity function, right? So it returns you the lambda xx. Okay. Now, if you do this, you realize that after that you compose this to this thing, you have this lambda x squared. Okay. Similarly, essentially, of course, it ends up being this whole chain. Okay, if you work it out. Okay. So rcomp essentially just composes the same procedure n times. Okay. So now let's try to, okay, so you understand the left side is exponentiation, e to the n. The right side is rcomp. Okay. So, and obviously the two guys are very similar. Okay, you can see the similarities, right? Okay, so the question is this. I would like you to define expt b to the n in terms of rcomp. Is it possible? Anybody? Agree? Is it possible? Possible, right? Has to be possible, it looks kind of similar. So how do you do this? Anybody? Like this, correct or not? Right. So essentially, the f, right? F, you replace it with a lambda that multiplies n, right? So if you do that n times, obviously you have the right answer. Is that right? So who agrees to this? You agree? Agree. Sorry, no. Sorry, so moral story is this. Don't always believe me. Okay, so obviously, okay, so this one looks right, but it's not quite right. Why is it not right? Okay, so, to be honest, there's a way of doing this, right? But obviously this is not right, okay? Now, the way to understand this is the following. So if you want to make the left side equivalent to the right side, they must all be equivalent, right? So what does expt 2 to the n return? 16, 24, 64. 2 to the 4, right? Which is 16, right? Okay, but that's a number, correct? What does rcomp return? Rcomp returns is just a procedure. So, prima facie, there's no way the two guys can be equivalent just by the functions alone, right? Okay. So the key lesson here is that you have to look at a procedure, and also, okay. So the thing about scheme is, okay, in most languages, they are typed. It means you can't get this wrong. The compiler will complain and tell you something is wrong. Essentially, the return type is wrong. Scheme basically is not a type system, so you can return anything you want. Okay, but note that you must be mindful of what kinds of return values, what is the type of the return value. Okay, to be honest, I think you're doing this mission 4, mission 5, right? Where they ask 4, is it? Mission 4, they didn't do all the types, right? Correct. Okay, so this is a lesson on types. It means you must be careful what it returns. It turns out that you can do this, right? You can define expt b to the n as what? Rcomp lambda. That's the same thing. Okay, it means you can define it as rcomp of lambda x times b. Okay, n minus 1 times applied to b, correct? Okay, makes sense, right? So essentially what you're doing here is that you take a start with b, okay, and you repeat the operator of multiplying by b n minus 1 times. Why not n times? Because you need antithesis of the b, right? Okay, so this is what you can do. Okay, and if you do this, you have you can basically work out. It looks like this. Okay, so it works. Okay, answer 16, obviously. Now, so you can generalize this into this form. Okay, you can do basically you can do a more generalized form of exponentiation where you can make it a, b, and n. Okay, and then essentially you start with a, you multiply b n times. This is to avoid this weird n minus 1 times kind of thing. Okay, all right, and you can do this, and then if you have this form called expt, okay, a b to the n. Then expt b to n will express as what? expt 1 bn, right? Okay. So this will be equivalent to this, right? Are you clear? Okay. So there's nothing special here. I'm just showing you some essentially identities, equivalent. Okay. Now next, suppose you have the following operation, binary operation. Binary means that you have operator that basically operates on two things. Okay, so here you want to compute this again exponentiation, right? A times A n times. No, not n times. A times A times A, the n of this A. Okay, so you also get having this thing n minus 1 times. Okay, so this is obviously the truth. This is what you get, right? A is let's say A is 2, B n is 5. Then you can do this. Okay, to compute this, right? Now, it turns out that we can turn this into a pattern called together copies of, okay, f and a, okay, and you can define it in the following form, which is what you saw earlier, right? Essentially, you want to apply the function a on function f on the f a x, okay, n minus 1 times on a, okay. So f is here, and obviously in this case, right? In this example, your f maps to what? Star. Okay? Alright? So this thing can be also re-expressed in this form. Okay, what am I teaching you here? I'm showing you that the same expt b to the n, b to the e, can be re-expressed in terms of different forms of other more complicated functions. Okay? And then it turns out that this together copies of will work for the picture language as well. You can go and basically stack 3 across DBs using this thing. Okay? So the point here I'm trying to make here is that this kind of composition, right, need not only be applied to numbers. You can also apply it to, like pictures. Okay? Now, let's take a look. So let's look at another example. Suppose now we have a slightly, this example is quite simple, right? Because it's all the same n times. Let's look at this slightly more complicated function. Okay, suppose you have this function f, okay, and you want to compute this particular thing, right? F0 to Fn, okay, and it's not a plus, it's not a times, it's this funny, operator, sum operator, all right, and there are n binary operations. Okay, so there are actually how many terms there? N plus 1 terms, right? You start from 0, you end up at n, right? So you apply the binary operator n times this operator. Okay, so I call it fold. Okay, I call this operation fold. Okay, and there are 3 things here. Obviously, there is number 1, there's operator, there is a function, and there's n, which tells you how many pieces, right? Okay, so how do you write this thing? So obviously, right now it's all recursion, right? We always do recursion. So what's the first thing in recursion? The base case, which is what? N equals 0, right? Then you do what? Return 1. F0, right? Okay. So you know that when n is 0, it means the operator is applied 0 times. You just return the first piece, which is F0, right? No brainer, right? Okay. After that, if you not do what? You will opt the Fn and the recursive call, right? Okay. So in other words, if it's not one piece, you will do this and you will fold it into the remaining stuff, right? Okay. All follow. Alright, this is a very basic application of recursion. Okay, so this F0 is this thing, right? Fn is the last term, okay? This whole part here is this part, right? And then this opt operator, right? Clear? Okay, very good. Now, okay, cool. Now we're going to define expt b to the n in terms of fold. Okay, how will you do that? Can you do that? Okay, fold is given here, right? Fold this thing, this thing. So what I expect you to do is to define expt b to the n in terms of what? Fold something. So the thing you need to do is to figure out what? Figure out what to put in for opt, what is f, and what is n. Okay, tell me, what is opt? Star, right? Quite easy, yeah? And what is f? Lambda x. Return b. Dx times, no. Okay, let's take a look. First time, second is what? Lambda x return b, right? So it means the f is a constant, regardless of whatever number index you throw inside, you put in a b. N is how many? Minus 1. Okay, because you need to multiply the thing n minus 1 times. Right? Because you have n pieces, right? Okay, good. So how do you do this? The way to do this is it's a pattern matching kind of problem, right? So this is the thing you want to compute. That is the fold, okay? Then essentially you want to figure out, okay, you need to match these two guys, match these two guys, match these two guys, okay? And that's why you know that F is this thing, all right? And then after that, you want to basically match the op, right? You realize op is this thing, right? And then after that, you need to match N, and essentially you need to count. Okay, this is how you figure it out. So it's not rocket science. You need to look at the thing you're trying to compute. Okay, look at the generalized higher order procedure that we give you, and try to essentially, it's like a puzzle. Try to figure out what piece is what piece. So I've shown like 4 or 5 ways of doing expt b to the n. All right. But the whole point here is to train you in thinking, okay, about how to write this in different forms. Okay. So remember all these questions from the last lecture, right? So we asked you to write these different things. Okay, let's define this one, sum of digits. How would you use fold to do this? Fold plus lambda x what? Da-di-da. Okay, it turns out you must return k digit of n. Okay, and you must count digits. Okay. So how you do this? You go and try to do it yourself. Okay. So essentially, you can do this. You need to write these two helper procedures. Okay. So for kicks, you do this yourself. All right. Next, product digits is like this, right? Obviously, right? Basically, if you can sum the digits, if you sum digits this way, okay. Obviously, if you change the plus to a star, you have the product digits, right? Okay. Now, then if you want to do square root digits, you do what? You add a square root here, right? Clear now? Alright. So what I'm showing, okay, I asked 3 questions, right? Just now. But the part I'm trying to show you here is what? The 3 questions are very similar, right? Okay. So what you do now, look at this thing, okay? And then just recap quickly. So last week we also did this thing, right? Some of the integers. Okay, I will be faster a bit because I'm a bit slow now. Okay, then this thing is like this, okay? And we can obviously do the same thing, right? That means instead of using this, you can actually create this thing called a product. Okay, and then put in some parameters to actually make this thing. Okay, and this one will actually be what's this? Your higher order procedure, right? Similar to sum. Okay, so if you look at these 2 procedures, it means one of them is your sum that you saw last week. Okay, the other one is a procedure that I just created to solve the other product problem. Okay, you see this is the form. Okay, now obviously the first thing to notice is obviously base case is different. Remember we just did this problem in class, right? Whereby you're multiplying things. So the base case, the 0 thing for the sum will be 0, right? But for multiplication you cannot have 0, right? Because everything's 0, right? So these 2 things are different. The base case is different. Okay? The operator obviously different. Okay? What else is different? These are only 2 things, right? Pretty much. So one thing obviously I can do now is to do what? I can add in operator. I can add in base case. And now I can create a new higher order procedure called fold2. Okay? And I can obviously define sum as what? Fold2 plus term A, next B, 0. And then your product will be what? Fold2 star and so forth, right? Correct? Okay, so the point here to note is this. The scary part is that you can keep doing this, right? So you can have higher order procedure of higher order procedure. And you keep doing this pretty much as it's like turtles, there's turtles all the way down, right? Okay. Alright, so basically it's like so the thing to note is this. It turns out that we can sort of like come up with infinite kind of possibilities for this kinds of sorry. Okay. It turns out that we can come up with different forms of this kind of fold2, whatever. Okay. Now and it's not unlikely that given where we're going, right, it's not unlikely that in exams you will find this kind of things whereby I give you this random stuff, this weird looking thing. I give you this other thing that's kind of more I don't know, familiar. and I ask you to express this familiar thing in terms of this odd-looking thing. Okay. So the point is this: you are not required to remember any of this definitions. Okay. You are required on the fly to look at this weird definition that I give you and to figure it out. How fun is that? Cool, right? Fun. Okay, so guys, I showed you like 4 or 5 ways of doing EXP today. Okay, so as I said, we give you some weird looking forms, and you hopefully will like it. Okay, so the thing to keep in mind. Okay, now it's already your end of the 3rd week. Okay, I think our progress this year is quite good. All right, a few of you are a little bit behind, but we will send email and try to help you if you find that you're having trouble. Okay. But most of you are zooming ahead. What's the highest level now? 14, 15 already. Okay. Very good. So this is only week 3, like level 15. Okay, but don't worry. The leveling gets harder as you go along, obviously. Okay, this is kind of the, basically sucking you in, right? Part, right? All right. All right. So anyway, the whole point is this: please do the homework, because this is where you need to basically learn the stuff. Okay, and one thing I want to say is this: don't be too caught up in leveling, and then anyhow do and just level and call it a day. You have to go and actually learn the stuff. Otherwise, the exams will come and bite you. Okay, how many have used the exams already? I'll upload like 30 or 40 exams, past exams. Nobody, okay, very good. So all no time, right? Never mind, you all will enjoy this later. Okay, so the thing to highlight here is that it's not about answers. So the answers don't matter. Okay, it's about the process. Okay. Okay, so what we have seen is that scheme procedures are first-class objects. They can be named by variables. Okay, they can be passed as arguments to procedures. They can also be returned as the result of procedures. Okay, so there are only 2 things. This lecture is very short, which is a good thing because I'm having so much trouble. Basically, you need to go and understand, how this higher procedures can be used to define specific procedures. So if you look at sum, for example, sum is actually a specialized form of flow-through, right? In the earlier example, and you can use sum to define more specialized procedures, which will compute certain specific sums. Right. So the point now is that you have to understand how to use higher procedures to define specialized functions. Okay. And this one is not a memory work thing. This is really a puzzle. Right. So I say again, in case I was speaking too fast earlier, you missed it. What you do is that you have the higher procedure. Okay. You write out what it does. Okay. You have your specialized version. You also sort of write out what it does. Okay. And really, it's a pattern matching exercise. Okay. And also, one thing is this. Last time, remember, you guys asked me, right, about lambda, right? Okay. This is one case whereby you won't use the define, right? Because you need to put in a lambda as an argument. Okay, and it's a bit lazy to go and define it, name it first. Okay, obviously you can define something, call it something, and then stick it inside, right? But no need. Okay, over here is where you use a lot of these anonymous lambdas, anonymous procedures. You just stick in there and hope it works. Okay? So the other key idea here, okay, in this higher procedures is this idea of the pattern. Okay? That means you must be able to look at these procedures which all do similar things. Okay, they're similar patterns. Okay, and hello sir. That's excited, The leveling also. Okay. The thing to do is to look at these procedures, that are different but similar. Okay, and the key idea again is the following: is to identify the parts that are different. Okay, and those parts that are different, what you do? You abstract them as a new parameter in the new higher procedure. Okay, so these are the 2 key ideas that I actually want to explain. Okay, so today, after this, so product is a new higher procedure that I just defined earlier. So the question now is how we define factorial in terms of product. Okay, and next thing is how we define expt in terms of product. So we have defined expt in 6 ways, 5, 6 ways. I lost count. Okay, and it's something that you should learn to expect. Okay, pretty much that's it. Sorry, see I accelerated too much. So what happened? Yes, question. let's take a look. Sorry. Okay, what happened today now is that my timing is a bit off because I was kanchiong, because I was slow, then now I'm a bit too fast. So let's go back. So your question is what? Compose. Okay, so compose does this, right? Oh yeah, compose does this. Okay, so your question is, what's the benefit of using compose to do what? Compose actually is predefined. I think it works, yeah. But it's very simple. Okay, so first of all, compose is actually predefined, I think, in scheme. But it is easily defined in this way. So your question is, what's the advantage? Oh yeah. So you have two pieces, it's not very useful, okay. But that's where you can actually do. That's why you can have this, right? Sorry, rcomp, right? So suppose, okay, you think about it. Suppose you have this function, this procedure, you want to apply n times. It's very painful to have to write this 10 times, right? So the way to do it is just compose. To basically and write rcomp as a procedure to basically compose n times. Then okay, so the point is, if you really don't want to use compose, you can, right? It's just that compose, compose, to be honest, is not very important, right? But compose does do what? Compose actually emulates this thing, right? Because in math, you can compose functions together to create new functions, which are like, fg, which is the f of g of x. So compose emulates this particular behavior, that's all. Same as this, Okay, so the question is, running time faster or slower? Same, I mean, actually, the two guys are doing the same thing, right? It's the equivalent, yeah. So, but the point here is that, okay, again, in programming, right, the whole point is what? The whole point is abstraction. What's abstraction again? Okay, abstraction basically, a big part of abstraction is information hiding, right? The whole point now is to basically not see stuff you need to see, okay? But abstraction is also a way of look at a problem, okay? And essentially, this allows you to actually look at this problem in a certain way that is convenient, okay? Helps you manage complexity. Okay, the whole point of this class, I say again, is to manage complexity. Okay, so far, the last 3 weeks, let me just sum up to this class. The last 3 weeks, we've done this thing called procedure abstraction. Okay, essentially, the general idea here is that you want to do some operations, okay? Right. And the problem is that if you write everything from scratch, it's very nasty, right? So essentially, what you do is you basically write a procedure, which is like a black box, okay? The black box is just separate what's inside from what's outside, okay? Basically, the outside box, all you need to know, all you know are just things, right? Essentially, you're looking at this procedure system, right? You know what the input, you know the expected output. You don't actually have to know what the box does, as long as the box does the right thing. Okay, so procedure abstraction essentially allows you to hide away the details of what's inside. Okay, and then allows you to use the procedures without without being confused. Now, then obviously what you need to do is not just to do this, right? You also need to basically be able to look into the box. So as the implementer of the procedure, then you're looking into the box. You don't care exactly what who's going to use, what it's going to use for. You just care that your box implements the operation it's supposed to implement correctly. Okay. Now, and then the point now is that higher procedures essentially is a much more, it's a higher idea whereby these boxes can be, basically used to generate other boxes. Okay. And also ideas on how you can take like things that's similar, right? And then actually generalize it into something that's more complicated, into more general. All right. So this is actually this ends what we call this procedure abstraction sort of idea. Okay, come next week, right, we'll be talking about data abstraction, which is another way of looking at the things you need to do, okay, of packaging this kinds of ideas, and then we'll be exploring a few of these abstractions. So OOP is also an abstraction, okay, which we'll cover again in a few more weeks. All right, so this ends this part. Any questions? Do you need something from me? What do you need? Okay, so those of you who are from Patrick's DG, come and see him. All right, the rest of you, take care. And those of you who are voting tomorrow, vote wisely. Vote for President Tan, right? Okay, all right. All vote for President Tan. Very good.